get started. Let's see. Yeah, I think it is started. Let's start. Yeah. So I'm at multi-dimensional grid and data. I think I need to go on something. Are you? Na 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 Let me add. Let me share my display. I think that would be much better. Yes, 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 yes. What is this? Are you? Do, 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 Okay. Window capture. This we don't need. Okay, so I think we got set up in OBS. So this is our code. I'm writing here side by side, practicing. We will go through it for theory, then we will see. So in chapter 2, what I did, I implemented a RGB to grayscale. Let me see. Is it? You can read it at least. Yes. Okay. So this is now we will start with chapter 3. It will teach us about multi-dimension and all that stuff. Alright, let's go to chapter 3. Okay, so multi-dimensional grid. Let me see, how can I open here the chat? Let me see, how can I open? Okay, so in chapter 2 heterogeneous data computing, learn to write simple CUDA launch, one-dimensional grid of threads by calling a function to pick elements in one-dimensional array, statement, executing threads. In this chapter, we look more on how threads are organized and learn how block, dimensional array, blurring, matrix multiplication. These are familiarize the reader with the reasoning. Reasoning about data parallelism before we proceed to discuss the GPU architecture, memory organization, problems contained upon multi-dimensional grid organization. In CUDA, all threads in a grid execute the same kernel function. They rely on coordinates, that is thread indices, to disguise themselves from each other and to identify the appropriate proportion the data to process. Chapter 2, heterogeneous computing. These threads are two-level hierarchy. The grid consists of one or more blocks. Each block consists of one or more threads. Basically, a grid, when we call a kernel function, you can say kernel is a function. Kernel name in GPU programming, we use that. So when we launch a kernel, we specify how many blocks and threads per block. So it's like a grid will have multiple blocks, and then we specify how many threads should be in each block. All threads in a block share the same block index, which can be accessed by block ID. Okay, these are thread index. Okay, thread executes, reference, variable returns, coordinates of the thread, execution kernel call statements, dimension, grid. These are available by grid dimension, block dimension, variables. In general, a grid is a three-dimensional array of blocks. Okay. And each block is a 3D array of threads. Okay, when calling a kernel, the command specifies size of each block. These specify using execution configuration parameter in the kernel. Call the statement of other execution configuration parameter specify the dimension of the grid, number of blocks, or block threads, parameter dim3. Each such parameter has dim3, which is an integer vector type of type three elements x, y, z. These three elements specify the sizes of the three dimensions. The programmer can use fewer than three dimensions by setting the size of the unused dimensions to 1. For example, the following host code can be used to call vector add kernel function and generate a one-dimension grid that consists of 32 blocks, each of which consists of 128 threads. The total number of threads in a grid is this. Okay, I see. So like this dim3 grid, we can create our like dim grid and block. Note that in a host code variable that are defined by programmer. These variables can have any legal C variable name as long as they have a type D3. For example, following statement completes the same result as statement above. The grid and block dimension can also be calculated from other variables. For example, the kernel call can be written following. This allows the number of blocks to vary with the size of the vector so that the grid will have enough threads to cover all vector elements. In this example, the programmer chose to fix the block size at 256. The value of variable n at kernel call time will determine dimension of the grid. If n is equal to 100,000, the grid will consist of 4 blocks. If n is equal to 4,000, the grid will have 16 blocks. In each case, there will be enough threads to cover all the vector elements. Once the grid has been launched, the grid and block dimension will remain the same until the entire grid has finished execution. For convenience, CUDA provides a special shortcut for calling a kernel with one-dimension grid block instead of using dim3 variable. One can use arithmetic exponent to specify configuration wondering. In each case, CUDA compiler simplifies the Simpler takes the arithmetic expression as x dimension and assumes the y dimension r1 given the current star. Reader who are familiar with C++ would realize that this is shorthand convention for 1D configuration takes advantage of how C++ constructors and default parameters work. The default values of the parameter to dim3 constructor are 1. Then when a single value is passed with dim3 vector, the value will be passed to the first parameter constructor, while the second, third parameters are the default values of 1, resulting in the So as was within the kernel function, x values grid dimensions are pre-initial according to the values of configure. For example, if n is equal to 4000, reference is to grid x and y in the vector will be 16 to 56 respectively. Note that unlike the three variables in the host code, the names of these variables within the kernel functions are part of the CUDA C specification and cannot be changed. That is, the grid dim and block dim are built-in variables in the kernel and always reflect the dimension of the grid, the blocks respectively. In CUDA C, the allowed values of grid dimension. So in CUDA C, allowed value of grid x ranges from 1 to the power 31. Okay, and those of grid y and z ranges from 2 to the power 16. All threads in a block share the same block idx, block y, z. All threads in a block share the same block idx, block idy, block id z values. Among blocks, the x value ranges from 0 to -1 and the y value ranges from 0 to -1. Z value is given this. Now we turn our attention to configuration of blocks. We now turn our attention to configuring block. Each block is organized in a 3D array of threads. Two-dimensional block can be created by setting block dim to z to 1. One-dimensional block can be created by setting both dim and y to 1. As in the vector add kernel example, as we mentioned before, all blocks in a grid have the same dimensions and sizes. The number of threads in each dimension of a block is specified by second execution configuration parameter the kernel call. Within the kernel, this configuration parameter can be accessed as x, y, z fields of block dim. The total size of block in current CUDA system is limited to 1024 threads. These threads can be distributed across the three dimensions in any way as long as the total number of threads does not exceed 104. For example, can be accessed. Okay, so it says. For example, block dim. So, okay, grid will have multiple blocks, blocks 0, 0, blocks 1. So basically, either you can have like, if you set just one value like 10, then it would be like one, all blocks would be on this way. But if you want to set multiple, then it would be combined basically. So you do 16 this side, or you set it 2 by 8 or 2 by 2 by 2 to x-axis. You say okay, block 1 says okay, value of 5, 12, 1, 8, 16 are all allowed, but 2, 2, 2 is not allowed because the total number of threads would exceed 1024. So total number of threads should not exceed 1024. Okay, a grid and its block do not need to have the same dimensionality. A grid can have higher dimensionality than its block and vice versa. For examples, shows a small toy grid example of this. Such a grid can be created with the following host code. Grid consists of 4 blocks outlined into 2 by 2 array. Each block is labeled with for example, block has id note that the ordering of the block and thread labels is such that the highest dimension comes first. The notation uses a ordering that is the reverse of that used in C statements for setting configuration parameter, in which the lowest dimension comes first. This reversed ordering for labeling works better when we illustrate the mapping of threads coordinates into data indices in multidimensional data. multi-field x coordinate, y coordinate, z coordinate illustrates the organization of threads within a block. In this example, each block is organized into an array of threads. Since all blocks within a grid have the 16 by 16 block, using a 2D thread grid to process a 62 by 76 picture. Same dimensions, we show only one of them. Expand block 0, 0 to show that it's 16 threads. For example, thread 0 has index y. Note that in this example we have 4 blocks of 16 threads with a current total of 64. We use this small number skip less to time per typically it is thousands to millions of threads. The choice of 1D 2D is usually based on the nature of the data. For example, a picture are 2D pixels. Using a 2D grid that consists of 2D blocks is often convenient for processing the pixels in a picture. Shows such an arrangement for processing a distance image picture P62 pixels vertical y direction and 76 picture in the horizontal or x direction. We will refer to the dimensions of multi-dimensional data in descending order: z dimension followed by y and so on. For example, for a picture of n pixels in the vertical y dimension, m pixels in the horizontal, we will refer to it as x n by m picture. This follows the C multidimensional array indexing convention. For example, we can refer to pyx as pyx in the text figure for consciousness. Unfortunately, this ordering is opposite to what order in which the dimensions are ordered in the dimension D. Block dimension, the discrepancy can be especially confusing when we define the dimensions of a thread grid on the basis of multi-dimensional array that is to be processed by its threads. Okay. X direction. Assume that we decide to use 16 by 16 block with 16 threads in X direction and 16 threads in the Y direction. We will need 4 blocks in the Y direction and 5 blocks in the X direction, which result in 4 by 5 20 blocks as shown in the figure. The heavy lines marked the block boundary. The shaded area depicts the areas that cover pixels. Each thread is designed to process a pixel whose y-x coordinates are derived from its block ID, dimension ID, and thread ID variable values. Vertical row coordinate, horizontal. Okay. For example, the pin elements to be processed by the thread or block can be identified as follows. Note that in figure 3.2 we have 2 extra threads in the y direction and 4 extra threads in the x direction. That is, we will generate 64 by 80 threads to process 62 by 76 pixels. This is similar to the situation in which a 1000 element vector is processed by the 1D kernel using 64 threads blocks. Recall that an if statement in this is needed to prevent the external threads from taking effect. Similarly, we should expect that the picture processing kernel function will have if statement to test whether the thread's vertical and horizontal indices fall within the variant range of pixels. We assume that the source code uses an integer variable n to track the number of pixels in the y direction and another integer variable m to track the number of pixels in the x direction. We further assume that the input picture data has been indeed or picture is allocated in the device memory and can be accessed through a pointer variable p out d. The following host code can be used to call a 2D color to grayscale conversion to process the picture as follows. In this example, we assume for simplicity that dimensions of the blocks are fixed at 16 by 16 dimensional grid. On the other hand, depends on the dimensions of the picture to process 1500 by 2000 of the picture. We would generate the block 94 by y x-axis within the kernel function references to grid dimension will result in respectively. Before we show the kernel code, we first need to understand how C statements access elements of dynamically allocated multidimensional array. Ideally, we would like to access PD as a 2D array in which an element or at row J and column I can be accessed as pin. This is however the answer is rendered on the basics of CUDA was developed requires a number of columns in P to be drawn and compiled for T to be accessed at 2D array. Unfortunately, this information is not known at compile time for dynamically allocated arrays. In fact, part of the reason why one uses dynamically allocated arrays is to allow the sizes and dimensions of these arrays to vary according to the data size at runtime. Thus, the information at the number of columns in a dynamically allocated 2D array is not known at compile time by design. As a result, programmers need to illicitly linearize or flatten a dynamically allocated 2D array into an equivalent 1D array in the current CUDA scene. In reality, all multidimensional arrays in C are linearized. This is due to the use of a flat memory space in modern computers. See the memory space sidebar. In the case of statically allocated arrays, the compilers allow the programmers to use high-dimensional indexing structures such as PMPP to access their elements. Under the hood, the compiler linearizes them into an equivalent 1D array and translates the multidimensional indexing syntax into 1D offset. In the case of dynamically allocated arrays, the current C compiler leaves the work of such translation to the programmer, owing to lack of dimensional information at compile time. One question: if, for example, what they're pointing is that any multidimensional array is like a single linear array in C. So that's what I implemented using in chapter 2 grayscale. So I just used a single array. One experiment I want to do is that array C is that, let's just say studio patch. I think that's all I need for now. You can make it, let's make it main, and let's just allocate a float array, and let's just say array malloc float and then equal to, let's just say 1000, let's just say 100. And what we need to do is that we need n into size of float. And then we want to let's just say we try to access memory out of what we have allocated. What will happen then? And let's just say here also. No error. So let's just say we try to access more than what we allocated. Oh, corrupted top size. So it says code down. So there now it is that error. Let's try to do is we will ask ChatGPT about it. So it can give us more information on what it is. Message. Are you? So. Okay. Error message. Okay, indicates that there is a heap corruption issue in C, which is caused by improper memory handling. Some common causes include buffer overwriting beyond the allocated memory, double freeing memory that has already been freed, use after free accessing memory after it has been freed, memory leak with heap corruption, writing past the allocated heap memory boundary on initialized boundary, using pointers without properly allocated memory, writing to feed or invalid memory location. No, 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 no. Are you coming to then inside GTB? Okay. Run with address sanitizer. Yeah. If you're using GCC line compiler program with this, provide detailed memory corruption information, analysis, check your response. Okay, they say that pass this while compiling. Okay, that sounds good. Let's just try this. Shadow byte represents 8 application byte this. He fled read John. It does point out that wow, nice. How much it can, so we did 101. Let's try that. So let's just try simple. We can access memory. Access it way long. It's just we are not able to write. We can see right here it is. What if I do it 4000? Now I start getting 7. It means when it enters into somebody else's territory, then only we get that error. Let's just keep it till 2000 and try to increase this one. We'll see how far we can go. Oh, just a few we can write. So sometime maybe we can pass on that. No. Okay. Makes sense. Okay. All right, makes sense. Okay. Memory space. A memory space is a simplified view of how a processor accesses its memory in modern computers. A memory space is usually associated with each running application. The data to be processed by an application and instructions executed for the applications are stored in locations in its memory space. Each location typically can accommodate a byte. Each location typically byte has an address variable set for multiple bytes, 4 bytes for float, and 8 bytes were stored in consecutive byte locations. When accessing a data value from the memory space, the processor gives the starting address of the starting byte location, and the number of bytes needed. Most modern computers have at least 4 GB byte-sized locations where each G is this. All locations are labeled with 2 to the power 30. All locations are labeled with an address that ranges from 0 to the largest number used. Since there is only one address for each location, we say that the memory space has a flat organization. As a result, all multi-dimensional arrays are ultimately flattened. Tend to equivalent to one-dimensional arrays, while a C programmer can use multi-dimensional array syntax to access an element of a multi-dimensional array. The compiler translates these accesses into a base pointer that points to the beginning element of the array, along with a one-dimensional offset calculated from these multi-dimensional indices. There are at least two ways in which a 2D array can be linearized. One is to place all elements of the same row into consecutive locations. The row are then placed on one. The two ways in which array can be linearized. There is one row consecutive. The row then placed on another element space. It is called the row measure layout. To improve readability, we used MJI to denote its element of MJI row, and then there is a column is equivalent to C expression JI but slightly more readable. Shows an example in which alpha movement linear into 16 all elements of row 0 first, followed by the 4 elements of row 1, so on. Therefore, the equivalent index of this column major layout. The first items are right element example indeed. Another way to rearrange the 2D array is to place all elements of the same column in consecutive locations. The columns are then placed one after another into the memory space. This element called the column major layout is used by Fortran compilers. Note that the column major layout of an 2D array is equivalent to the row major layout of its transposed form. We will not spend more time on this except to mention that readers whose primary previous programming experience should be aware that C uses row major layout and then column major layout. Many C libraries that are row major. Row major layout for 2D C arrays. The result is equivalent to 1D array accessed by an index expression. This or an element that is in the jth row and ith column of an array with element in the row. As unsigned char, 8 pixel is 3 consecutive chars for 3 channels. Color to grayscale variant, This is blog launch and thread hero. Okay, I think that's all for now. I'm going to